Okay, so in the last class we discussed quite a few physical mechanisms that may explain why electrons would like to pair up or get correlated or attracted to each other rather than being repelled according to the Coulomb interaction. And one of the mechanisms we did talk about had to do with the lattice distortion and the phonons, and how that can at least qualitatively and also semi-quantitatively explain the reason for pairing of electrons. And one of the pictures that we came up with and a physical reasoning for was that if I have two electrons with energies E k and the other electron with E k prime, and the difference of the two energies is plotted here. And what we saw was if the phonon energy is h bar omega that they exchange, then the interaction or the lowering of the energy of the two electron system because of the emission and reabsorption of the phonon with k and let's say upspin and k minus k and downspin. These are the two electron states, and they scatter into k prime upspin and minus k prime downspin. Right? So if for this process the energy lowering looked something like this. So essentially if the difference was larger than the phonon energy, you have to pay a price in energy, but if the difference of the two electron energy is lower, then you are the net energy of this whole process is negative. That means it can lower the energy of the total electron distribution. So, and and this can happen. This energy of the phonon can change, and it can be very low energy phonons or high energy phonons. And one of the ways to look at it is the highest phonon frequency that is possible in a crystal is what's called the Debye frequency or the Debye energy. And so the Bardeen-Cooper-Schäfer theory says that I'm going to simplify this picture completely, and I'm going to assume lowering of energy that looks like this. I'm not going to bother about all the details of exactly how much it is and all, but I'll assume that the lowering of the energy is that much, is constant with respect to the difference of the energies of the electrons, and this is minus V naught. This is the energy lowering due to the interaction. If you do some of the microscopic numbers and such, it'll come out to be of the order of 1 millielectron volt or something like that, order of magnitude. So that's the point where we want to pick up, and today what I wanted to do was finish that discussion and explain the problem of Cooper pairing, and do it quantitatively now, and show that because of this interaction, this is just, we have looked at just two electrons interacting with each other, but remember we have a lot of electrons on the Fermi surface, and so we must include all of them and show why there's a phase transition. That's something we want to show. First we will just look at this picture and show that quantitatively that the lowering of the energy of the electrons that are contributing to the transport in the superconducting state, we will quantitatively calculate it, and we will get this result that in the electronic energy spectrum, the total lowering of energy will be something that I wrote down earlier, which is 2 times the Debye frequency times exponential times density of states at the Fermi level times this V naught here. we are going to get that. So this will be the lowering of two particles on a Fermi surface that are interacting with that attractive potential. It's not, so I'll discuss that and then show that that's essentially the reason for pairing, but then we will look at the full, the BCS wave function and show how that gives us the, how can we write down the state of the system that's in the superconducting phase using a true many-body wave function. Here, even with two particles, we can explain the opening of the superconducting gap. But in a normal superconductor, in a superconductor, you have 10 to the power 20 some carriers, 10 to the power 20 some Cooper pairs, not just one. And we're going to make that transition to the BCS and show how they used a very ingenious trick to, rather not a trick, constructed a very ingenious wave function for this entire many-body state, and then were able to calculate from there all the transport parameters, the thermodynamic parameters, the lowering of energy, etc., all of those quantities. Okay? And then this is obviously a very rich literature. I wanted to give you a flavor of this and show you what sort of thought process, how many body or many particle correlated transport really how to think about it. What are the best tools available to us to think and understand transport where it's correlated and many body in this. So that's the spirit in which we are covering this. This is a lot more detailed to what we will, and you can read more. But I wanted to give you the fundamentals of this theory. And here we will see that you will need to invoke, you have in your earlier assignment where you did the the creation annihilation operator formalism will be of great help here. It will come in here, and we'll use it for the last 6 or 7 classes for the other topics we're going to cover. So, and then I think I'll be able to finish this part today, and I'll just give a quick introduction to a relation between, or an apparent relation between superconductivity and the next topic we're going to cover, which is the beginnings of the topological insulators, which is integer quantum Hall effect, and we'll kind of motivate it from here. So that's what we want to do today. Okay, so let's start with the Cooper pairing problem. Here, if you remember, what we were discussing is what happens in a normal metal. And when I say normal metal, today we can cause this to happen in a two-dimensional metallic crystal, or even in some semiconductors like the chalcogenide 2D layered materials. You can actually, with field effect, remember when we talked about ballistic FETs, we had a gate, and with the gate we could change the number of electrons in the conduction band or in the valence band with field effect. Today what people are able to do, and in fact it's rather new, only was done in 3 or 4 years ago, in a two-dimensional semiconducting crystal, with the field effect you can pull up the electrons, rather you can put so many electrons in it that it becomes reasonably highly metallic, and then when you take it to low temperature it becomes superconducting. So in other words, with a field effect you can make it transition from superconductor to normal metal with a field effect now, and that's very interesting. So of course you can do it with temperature, but you can also do it with field effect now, and then that's kind of very interesting. All of these still happen at low temperatures, 10 K or something like that, but right. So but it does, and it's there's a relation between superconductivity and semiconductors in that sense. Okay, so so here's the problem now. We are, and this was really the breakthrough of Leon Cooper, who was able to explain why two electrons on a Fermi. So if you remember what we had drawn earlier, was this is the K space of electrons that are occupying the normal states of a metal. So these are k is equal to 0, and all the way up to the Fermi surface or the Fermi energy, the states are occupied, and below that they're occupied inside the sphere, and outside that they're mostly empty. We're at low temperatures, so the distinction or this transition is relatively sharp. And now the question we're asking is, if I take an electron on the Fermi surface with a momentum k and spin up, and I think we had also argued in the last class why, if there is pairing and interaction strength of minus V naught, the largest number of such states you can get are if they're diametrically opposite. So that's something we're talking about. And you can also look at the surface of the sphere compared to if there were pairing of this and this, then you only get a ring here rather than the whole surface. So that was one of the arguments why the pairing will be favored for states that are diametrically opposite on the Fermi surface. Right? Now the game is the following. In the single particle picture, we are not invoking any many-body physics right now, just two particles on a Fermi surface, two electrons on a Fermi surface, and say that if they're in the normal metallic state, what is their total energy, right? In the normal metallic state, the total energy of these two particles is 8 square k square by 2m, and the k and minus k are the same, right? K and minus k are the same, so I get 2 times that, right? Right. That's the normal kinetic energy of these two particles together, right? A sum of the two, right? And this is, we can just call this quantity as E0 of k, which says that this is my normal metallic properties, no superconductivity, no correlated effect, none of that, right? Okay, so now what we want to do is ask that if instead of being independent single particles, if they pair, if they become a correlated state, what is the energy of this pair, right? And more importantly, is the energy smaller than this, right? Does that make sense? I mean, this is the kinetic energy. In fact, for t very close to 0, this is 2 times EF, right? Where both are on the Fermi surface. Right? Both are on the Fermi surface is 2 times the Fermi energy. And if you know the electron density of any metal, you know how to calculate the Fermi energy, right? So it's about 5 to 10 eV, right? Okay, so now, so here's the argument of that Cooper provided. That let's say that I write if they pair, then not the single particle, but the many particle or a 2-particle wave function now will look something like this, right? It will have both coordinates of where this particle is and where that particle is, right? And remember, the wave functions will be a product, right? Not the sum, but a product of the wave functions, right? So it will look like e to the power I k dot r1, right, times e to the power I. And see, the wave vector of the other is minus k, right? So it's minus k dot r2, right? Something like this, right? Yeah. And now this is the wave function of 2 particles, and there are many, there are many possible k values, not just this k, but there are other k values allowed, right? Possible k values. So in general, you would write something like this. It's a some coefficient linear, times the this is the product wave function of the two, right? So yeah.
So would there be like some 1 over n factorial, 1 over 2 square root of 2 factorial?
Yeah, I'm coming there. Right, that's right. So that's exactly right, and I'm coming there. So this is what you call as the orbital wave function, meaning the real space part of it. And in addition to that, there are the spins, right? And the way we have chosen here is the spins are up and down, but that's not the only possibility. Okay, they can also be down and up, right? Those are the 2 possibilities. And here, and this is a symmetrized wave function for 2, so it's vertical as a Slater determinant, but for 2 particles. And so you get, this is the spin part of it. Spin, and this is what's called a spin singlet, and this is the orbital. Okay, so the spin part of it in the singlet state, this is not going to, we are not going to introduce any magnetic impurities and such. So we are going to kind of, this is the simplest case. You can also have a triplet, spin triplet, where both are up spins and or down spins, or a combination up and down, right? And I think I'm going to leave that to one of the projects that Sayak is doing. He's going to talk a little bit about triplet pairing and all that. I'm going to just do the easy one, which is the singlet, which is what Cooper really solved for the first in his paper. And so this is the wave function, and the spin part of it will kind of tag along. It's not going to change anything, because we are going to only look at the non-magnetic features and such. And so but it's there, and then it's a singlet state, right? So now, how do you find the energies? Remember, the game we're trying to play is ask whether there's a net lowering of the energy because of the pairing, right? And how do I find the net energy of a correlated state like this? So this is a many particle state now. It's not a single particle state, right? Because it has wave functions of both, the product of the two. It has, remember, so it has energies of both phases. All that information is there now, right? Many body wave function now. It's the simplest. It's a two-particle wave function, and you can see it looks it's in a nice way, because the k and minus k are here. You can write it as e to the power I k dot r1 minus r2. So you can see that you're kind of being led to what's called a center of mass coordinate system now. It's immaterial where exactly r1, where particle 1 and particle 2 are. But what's more important is how far apart are they? The center of mass sort of there. Times spin factor, which is going to be like that. So that's your wave function. And how do we find the energy? You put it into the single particle Schrodinger equation, right? The Schrodinger equation, which and how does the Schrodinger equation look? It looks like P1 squared by 2 mass of particle 1. P2 squared by twice mass. This is the total kinetic energy of the two particles. And then you have a potential energy of interaction of the two particles, R1, R2, right? Whole thing times the wave function is equal to the energy that you're after times R1, R2, right? It's just a plain old, single particle Schrodinger equation, nothing fancy at this point. But we have taken into account that there are two particles and they're interacting. More importantly, this term is tying the two together. It's interacting. This is the correlation term, right? So if this was absent, it would be a trivial solution. It's just the sum of, that's what you get, right? But it's there now, and this pairing is, this is what we are microscopic picture for it here. Right. Right. Okay. So. Let's work through this part, and I don't want to spend too much time here, but I can actually take this whole thing and plop it in here. Remember P1, what does that mean? It means minus IH bar times d, but of R1. It's going to act on just the R1 coordinate, right? I mean, the R1 coordinate. And this is a double derivative. What's it going to do? It's going to pull out two ik's to the front. Right? That's what it always does. So let's write that down. You can see that the kinetic energy terms will just give you that again, right? These two terms will just give you that. So I get 2 times, let's just write it as E0k, okay? There 1, okay. Plus, and then I have a sum now, basically summing over all possible k's here. And then there's a v. I'm skipping the vector notation and all that. I hope it's clear what we're doing here. right? That whole thing is equal to, on the right hand side, you get E sum of k. I just rewrote it, just plugged it in here, right? And I think we didn't miss, and I canceled out the spin term. It's the same everywhere, so I just got rid of it, right? Okay, so now I think looking at this equation, you see that it's kind of begging for a Fourier. You just want to pull out the. So what you do here is you do e to the power maybe minus I k prime, and let's call this difference as just r. Okay. The difference as and you do k dot r, and you integrate it over all space and volume of all space. I mean the whole solid, physically the whole solid. That's the volume, and then you apply this operation on each term, right? And what does that do? It will just pull out the term with the prime here, right? It will just leave one term here, right? Because you get an integral which is d cubed r over I k minus k prime, right, dot r, and that's Kronecker delta k comma k prime, right? If this is 1, the total integral, if k minus k prime is 0, the whole thing is just 1, right? And if k minus k prime is non-zero, then the whole thing is 0 because it's oscillating. So that's the meaning of it, right? And so that just pulls out the terms here, and I'm going to just write down the solution. Except after this, I just need to kind of reindex k and k prime. They're dummy variables, so I'm just going to write it this way: 2 times E0 of k times g of k. I'm just pulling out the numerator term here, and I get a sum over k prime now. V of r e to the power I k minus k prime. I think probably r is equal to E times g of k. So remember, what are we solving for? The only unknown for us is the coefficient g of k. If I know g of k, I'm done, right? The problem is solved because I know my wave function and all that, right? And I can find energy, whatever you want, phase, momentum, current, whatever you want, you can calculate after. Once you know what are the g of k. G of k is the only unknowns, right? And so you look at this equation, and then you also realize right away, and I think this should also be clear, that this quantity is, sorry, I forgot to put down, you have to have the integral, right? D cube r over volume. I forgot that part. And when you look at this term, let me rewrite it a little more cleanly here. A sum over k prime, g of k prime. So this quantity here is just the Fourier transform of the of the pairing potential. Fourier transform of the pairing potential, and you can write that as just v of k comma k prime, or v k k prime. This is the Fourier component, right? Same units, because you see the volume of volume, so it's still in electron volts, if you might, right? So it's just one term, and then what you get is 2 times E0k times these unknown coefficients plus a sum over all the unknown coefficients times the interacting potential, or the pairing potential, is equal to the new energy that we are after times this, right? So this is a simpler equation now, and so you can just rearrange it a little bit and make this as the subject, right? Stick to the left side if you might, and then that becomes g of k is equal to a sum over k prime. And I want to go through this because this was this will appear again in the when we do the full-blown many-body BCS wave function. It'll appear again. So, but then I won't solve it again because you've already done that, right? So, all right. So you get a sum of g of k prime, get a minus v of k prime divided by Actually, let me write it this way. Okay, just that. And I hope this is clear what I'm doing. I get here E minus 2 of E naught, right? Sorry. Yeah. 2 times E0 of k minus E. Is that okay? So I've just rearranged it, the whole thing. I wrote this outside of the sum. Why? Because this is k, but the sum is over k prime. Right? So you are really not summing over this right now. This is actually a constant on the right side. Right? And at this point, we are going to invoke our, Cooper's approximation that this interaction potential is constant. It's not changing with k or energy or ek. It's not changing. It's just constant from 0 to h bar omega d over this window. It's just a constant. Does it make sense? I mean, we're just going to invoke that, and it is negative, right? It's an attractive potential. It's negative, and we have discussed as to why. I'm not going to try to justify that anymore. So minus of that is just V naught, right? Okay, so now this is the equation to solve. You want to find g of k, but you have to sum over all these coefficients on the right side. All these coefficients. This thing is outside of the sum. It's the function of k. And how do you solve it, right? What do you do now? Right? Now that's interesting, right? You look on the left side, and remember we are summing over like 10 to the power 20 states here, right? So it's a very large number of states. But if you look on the left side, you also have this thing. And if I sum on the left side over k's, right, 2, then I must, again, I'm going to also sum over this here, right? Right? And this is called the self-consistency relation. It's kind of very nice that it works out this way. And you realize that this thing is actually exactly the same as this. It's just different index, right? It just goes away, right? So this is the fact it went away is not going to give you a g of k, but it's going to definitely give you your energy, right? That's what we're after here, right? So it's the self-consistency relation. Is that clear? I mean, you just rearrange it this way, and so I think this was, if you have seen many resolutions of identity or one, this is a very interesting resolution of identity. How many ways to write one, right? So, yeah. But so this must hold, and that immediately kind of this has a very interesting implications now, and we're going to kind of look into that right now. Okay? But is that clear? So this is how where you end up, and I'm going to take this V naught to the left side, and then try to make a relation. And what we did here is actually it reappears in many different problems. Plasmons, sorts of resonances, deep levels in semiconductors, deep defects. This problem reappears many times, and the solution it has also reappears many times in many different, in many different phases and many different physical phenomena. Okay, so let's look at this here. So what is saying 1 over V naught? V naught is a attractive potential is equal to a sum over this whole thing, and this is unknown right now. Right? It's unknown, right? So what we can do now is make a plot, or rather, what was the game also is that what is the value of the unknown energies of the electrons? Is it lower than 2 times EF? That's what we're after. Right? Yeah. And we want to find out the solution to this. You can see that on the right side you have many terms. Therefore, if you want to solve it exactly, it's impossible, because, or I mean, if you want to solve it using polynomials, because you can write this plus that, and every time there's an energy in the denominator, your order of the polynomial goes up. Right? If I have only one term, it's just a linear equation. If I have 2 terms, it's a quadratic. 3 terms in 3rd order, 4th order, and so on. Does it make sense? Right. So this is the unknown for the problem. So what we can do though is make a plot of this, right? And that is a very useful thing to do. Make a plot. And let's make a plot of, as a function of energy, which is unknown. What is the total energy of the two-particle system, which is what we are trying to find. Right? And we make a plot of the left-hand side and the right-hand side, and wherever they intersect, those are the allowed energies. Right? And that's simple enough. If you did not have any interacting potential, right? What are the allowed energies? This blows up, right? And you must ensure that this also blows up, right? Right? Does that make sense? Right? And when will it blow up? Whenever the energy, whenever you're changing the energies, and whenever it hits the normal metal energies, it's going to blow up, right? Right? That means it's picking out the energies of the particle that are non-interacting. It's giving you the energies again. And it's, back to, you didn't have to go through this whole thing to say this. But now it's extremely powerful. This thing is what's called the Green's function of the system. This sum over the energies. It's really in every, it sometimes appears in more complicated forms, but in general, this is exactly what it is. The poles of this function are the eigenvalues of the system, right, where it blows up, right? It's a very strong response, or the impulse response of the system now, right? So the system will only allow energies where this function blows up. It's a very loud signal, right? So, and if you are off, it's going to be very low, or low value. So we can start looking at this and see that till so 2 times. Let's see, very far out to the right side of energy, very large energies. First of all, this quantity is just a constant, right? It doesn't change with energy. So let's sketch it maybe using this one, like this. That's 1 over V naught, and so it's just a constant. Right? Now we try to sketch this very far out to the right side. This thing is very large, right? And it's negative, because this is larger than that, very far out, right? Way larger than the Fermi energy, meaning your energy is out there, right? So in that case, this thing will kind of be like that, and it's a small number, 1 over E, small number. But as you come close to the Fermi surface, now you have states here, right? So you have 1 over, this minus that, and as you come close to 2 times Fermi energy, it's going to start blowing up, right? And it's going to blow up many times, as long as as many times you have particles, as many states you have near the Fermi surface, it's going to blow up that many times. And it's going to go to minus infinity, and then again start from plus infinity, and then do this. Do you see what I'm doing? And then there are many states here, okay? And here's one state. You detected one, right? And that's a solution, because let me use a blue color too for the. So what we are plotting is the right-hand side now. And what I'm saying is this function looks something like this. And then there'll be another one. It's essentially going to kind of be like that. Every time you go larger than allowed energy to lower than allowed energy, there'll be a plus infinity to minus infinity excursion of this function, right? And it'll continue till you reach the 2 times EF, which is the smallest, and then finally. Also, what you see is if energy is very large, very small, close to 0, well below the Fermi energy and all that, right? Then this quantity is much smaller than that, so this is actually positive, right? You see that, right? And for this, is that clear? I mean, so it really does not go to 0 below the smallest energies. So essentially what I'm trying to say is the last branch of this is going to look like this, the last branch, below the lowest energies of this. And that's very important. In fact, so those are all the energies allowed. So here are the allowed energies. And these are kind of close to the allowed single particle energies. But what this picture is trying to tell you is the following, that let's call this as 2 times EF. is the smallest two-particle energy. Remember, we are not going deep into the Fermi surface. It's only on the surface. We stop on the surface. Right? And on the Fermi surface, the energy is 2 times EF. Right? And what this problem is saying is that no matter how small is your attractive potential, right? If you make attractive potential very, very small, what happens? This thing actually goes up. Right? It'll go up more, go up more. But no matter how small you make it, this intersection is always going to be there, and it's never going to go away. Does that make sense? Right? And this energy is always less than 2 times Fermi energy. Right? So this is really the lowering of the two-particle energy compared to its free particle energy. It's just that this quantity here. Right? And it's saying that there is one solution which is lower in energy than 2 times EF. And this is pictorially what it is. Right? Is that clear? So and from geometry, you can see that you are guaranteed that there will be one. Right? You're always guaranteed here. Right? And it's very similar to the problem of particle in a box. If you have a symmetric box, you're always guaranteed one bound state, for example, in a 1D well, and it's very similar to that. So, is that clear? So, and now the job of actually finding what that energy is not very hard, because what you can do is look at this and say that. Now, is that clear, by the way? So, you can see the smaller this attractive potential gets, the lower is the this difference of the so this is your slight lowering of the system energy because of the pairing or the Cooper pairing. Okay, so how do we actually find the energy? So we can write it as 1 over V naught is equal to a sum over K's of 1 over 2 times E0 of K minus the energy I'm after. And I think you know that instead of summing, I can integrate it now because I have a large number of states. Okay, and what do I integrate over? I can change this sum to either an integral in K space, or you can sum it over energy space. Whichever. I'd rather go directly to energy space and write as the density of states as a function of energy, or let's write it as small e times dE. Right, and this is does that make sense? E is just the single particle energy. Okay, so you are integrating over energies. And what is the interval of integration? And that's very, very important here. Right? What's the interval of integration? Remember, we are not talking about inside the Fermi surface. It's only at the Fermi surface and a shell around it. The particles are interacting by emission and absorption of optical phonons, and the maximum phonon energy is h bar times Debye frequency. Okay, so you must go, this quantity can go from Fermi energy to Fermi energy plus the Debye energy, right? That's your, those are the limits of the integration. Right? Is that, at least, we can argue about that part, because if you go very deep inside, there's nothing to talk about. They're all filled and no action there, right? But this is it. Now, even now, the problem, yeah, John. Yeah, you could do that. You could do that. I'm not trying to. You could even write what John is saying is why not minus 2 plus. You can do that too. It'll give you pretty much the same answer. So just yeah.
Is the asymptote all the way to the right also at EF plus the Debye frequency?
Is the asymptote all the way to the right?
Yeah.
So here, you see, yeah, that's a good point. Okay. So what we have here is, this window, inside this integral, this window will have a width of, Debye frequency. Okay. It's basically 2 Fermi energy, or it will have 2 times h bar omega.
Yeah.
So, yeah. Okay. So now what is extremely, important here is that the density of states right near the Fermi surface. Remember, the Fermi energy is close to 10 eV, let's say, whereas the Debye frequency is maybe, max maybe 100 MeV or something like that, of the order of magnitude. Right? There's a very big difference between the two, right? And as a result, the density of states of the metal within this energy window is really not changing much. It's kind of, almost flat. And this quantity is very important to be able to analytically understand what happens, because then if the density of states is very close to the density of states at the Fermi level, it's not changing much at all, right? So you can pull it out too from this integral, and then you get a energy over 2 times, or whatever variable way you write it, times E from Fermi energy to Fermi energy plus h bar omega d. Right? So this you can write that. And all right, so and then this is, I can call this as the N0, just label it as that, the density of states at the Fermi, at the Fermi surface of the Fermi energy value. And then what we get here is 1 over N0 V0 is equal, or roughly equal to this integral, and that's basically a natural log integral, you can see from there. So natural log, what you'll get is 1 over 2, maybe a natural log of this minus this. So 2 EF plus 2 h bar omega d minus E over 2 EF minus E. That's the integral, right? Yeah.
Now, if you're doing this in like a constrained system,
good point.
Where, for example, dimensionality is lower.
I'll talk about that. That's a good point. Yeah, you're probably bothered about what if it's not constant. Mm-hmm. I'll come to that in a second. So, good point. Yeah. Okay. So from here, I think you see that it's not very hard now. You want to find that. Right? You just invert it. Right? Invert this whole expression. Take e to the power. That, right? And then after you do all that, I'm just writing it down. Your the new eigenvalues or new allowed energies is going to be 2 times the Fermi energy minus twice the Debye frequency energy, the phonon energy, times e to the power minus 2 over N0 V0. This is what you're going to get. And this is your final bound state energy of the system after 2 particles. And you can see now that indeed, because of this pairing, the energy of these 2 particle states are lowered by this much compared to if they were not interacting. And this is what we wanted to kind of show, right? What is very important to see here is that this expression has the form e to the power minus, if you look at the interaction strength, the particle interaction strength, it goes as e to the power minus 1 over that strength, or x. X is the strength, right? Now this function is what you call is a non-analytic function, meaning you cannot Taylor series it at all. Meaning you can't do perturbation theory on it at all. Why? Because if you take this as a function and you take f prime of x when x goes to 0 is equal to f double prime, and you can check it, okay, when 0, all of them are exactly equal to 0. They all vanish in all orders of perturbation. And that means this could have never been obtained from perturbation theory, because perturbation theory essentially is doing this sort of approximation, that what if it's small and I expand it around its value. And this is unachievable from perturbation theory. It's a first order. Basically, your total system eigenvalue has changed now, right? I mean, the system has gone into a different phase. So if you're trying to do perturbation theory, it's a phase transition, and it's not possible to kind of get here in that sense. And mathematically, it's clear why, because this function is not possible to Taylor expand. So. And this is why it took 40 years or 50 years for people to figure out, because most of people were trying perturbation theory, and here you can't get it by perturbation theory. You have to solve it exactly. Right? So one of the questions Andrew asked is, I made this approximation that the density of states is I'm assuming it to be constant, but of course I can go into say a 1D structure where the density of states is changing near a Van Hoff singularity or something like that very fast. There are large changes over small energy range, right? So indeed, let's see. For the 3D case, it's very clear that the let me sketch it this way. So for 3D, we have density of states like that. For 2D, you have a constant. 1D, it's changing like that, right? What really is important here is also N0. So N0 is the density of states. Okay, so if you look at it carefully, you also realize that this term, if the N0 times V0, which is the density of states times the pairing potential, if this term is too, this term is too small, okay, this term is too small, meaning if you, let's say I have some pairing potential of the order of 1 MeV, but I have too few electrons, in which case my total, this lowering would be exponentially small, and your TC would be very, very, very low. You'll never see it almost, right? So you need a lot of electrons at the density, at the Fermi level, right? And by the time you fill up a state to a lot of electrons, you are really high up in the surface. So in 1D, for example, you are really very high up here, and then again the change is very small. So it actually holds, or rather, wherever you see superconductivity, this actually holds. That's because the densities almost become constant at that surface. So yeah.
How do you change the interaction energy V0?
How do you change the interaction energy V0?
How do you obtain it?
Oh, how do I obtain it? So in this problem, we are making an assumption that it's a constant. How do you actually obtain it? You can probably look at the microscopic, first principles. Look at the plasmon frequency, because this depends on the electron-phonon interaction. So it'll depend on deformation potentials. If that's your pairing mechanism, then you have to appeal to the microscopic picture, and this would be related to your, deformation potential constants and phonon frequencies and so on, right? I've not tried to say exactly how you calculate it. I had given you some. You remember we were looking at some matrix elements for this. There was a rough formula for it, and the reason we got this was the formula for that was basically the Coulomb repulsion. I'll just write this down rather than try to explain. Times the phonon energy over Ek minus Ek prime minus h bar omega q. So that's how it looks, and this is essentially a q or energy dependent V0. But Bardeen-Cooper-Sheffer said, I don't care. I'm going to just assume it's negative and constant at this point. The order of magnitude is what's important. The exact details you can incorporate and not assume it to be a constant. You can keep it here inside, and do that.
Okay, and that it doesn't have to be for an electron-phonon interaction.
No, not at all.
Electron.
Yeah, actually, spin interactions in the more. It looks like the high TC superconductors. There are other pairing mechanisms, not necessarily phonons. But no matter what it is, there's a pairing. That's the game. That's the game we're playing at this point. But it's important what you asked. What is the exact nature of pairing mechanisms? This theory doesn't care almost. What it does care about in the end is what is the window of energies, and if it's phonons, we know it's the Debye energy window. That's yeah. Right, so okay. Any other questions? Yeah.
Does the pairing energy change from spin singular to triplet?
It does. It does. In fact, yeah, I'm not trying to cover, but yeah, for spin triplet, it would need a bit more work. You have to take care of the orbital part of the wave function and then a little bit more, but it does change. But the scheme stays the same. Of solving the problem stays the same. Right? So I'll just I'll just want to summarize this one more time, and then move to the full BCS part, because this is the heart of the matter, and then the BCS is another level of detail over it. Okay. So what did we do again? We started with a two-particle wave function, just use plain old two-particle Schrodinger equation. The big difference now is I have a correlation between them. Two electrons are correlated to each other. And then you kind of went through this whole business and wrote this, and essentially we have this total lowering. And this is really the reason that they would like to pair, because when each of those two-particle states can pair, they can cause a large amount of lowering of the total system energy. So that's the reason why they will pair. Okay, so the next what I wanted to do is point out that this little step, which is very crucial here, being able to make this constant and pull out. This has an analog in a problem that if you have done quantum mechanics courses, maybe you have seen it, maybe not, I don't know. But it's intimately tied to even a single particle in a box problem. Okay? So in a particle in a box problem, if you have a one-dimensional problem, x, and here's the potential, then you are guaranteed that there will be a bound state, guaranteed. And this picture is exactly the same as you can draw these. There will be a tan and all that. There will always be an overlap. You're guaranteed. There will be one bound state, at least. It can be more, but at least one, right? Now in a 2D picture, if I have similarly a potential well, maybe it's circular well, rectangular well, whichever way you look at it, right, or a hole in the wall. I don't know whether you have seen it or not, but it's slightly different. The answer is slightly different. And then in the 3D case, if I have a attractive potential in 3 dimensions, you are not guaranteed to have a bound state. So you're guaranteed here, you're not guaranteed here. Right? Sorry, you're guaranteed here, you're not guaranteed a bound state there. Right? 3D, or what does it mean? The attractive potential should have a minimum strength to be able to provide you a bound state, a minimum strength. And if you are below that, it will not allow a bound state. Here, no matter how small the strength, you will always be a bound state. Right? And the 2D is an intermediate region. And in the 2D case, you have what's called this logarithmic divergence. And this is what we encountered here, a logarithmic divergence in some sense. Because of this, you are also guaranteed a bound state. But it's exponentially shallow, which is, it's exponentially shallow. And if you solve the problem, what you'll see is it's related to, again, here. So I'm saying 2D, an electron in a 2D potential, no matter how shallow the potential, you are always guaranteed a bound state. Here, the bound state energy will go as linear or a function of the depth of the well, V0, right? Forget proportional to V0. I mean something like that. Here it is going as e to the power minus 1 over V0. Right? So that's what I mean. It's exponentially shallow, right? The depth of this, and then this is what showed up, what helped Cooper solve the problem. It's also basically what I'm trying to say is it has exact analog in a single particle, not even 2 particles, single particle quantum mechanics, particle in a box problem, and it's tied to that. The solution scheme is exactly the same. All right, just wanted to point this out. You can probably see that in a 1D, if there is a hole and there's an electron or any particle going around, you're bound to fall inside it. There's no way around it. In 3D, there are ways around it. The paths around it. So 1D, there is none, right? So that's a classical analog to it. The 2D is a little tricky to think of it that way. Okay, so now let's look at the second. Just also some numbers. I think we did a bit of math, but but let me give you some numbers. What is the N0 times V0 for most BCS sort of not high TC superconductors, but not most normal metals which become superconducting or alloys and all that? This is typically less than about 0.3. This product. So you get e to the power. So this is, so as a result, this is what you call as a weak coupling, meaning this number is not much larger than 1. It's actually quite a bit smaller. So you get e to the power minus a large number. Right? And that's why superconductivity is a low temperature phenomena, because this energy is of the order of the critical temperature. Right? This whole thing is of the order of the critical temperature, superconducting in transition temperature. Therefore, because this number is small, you have low TCs, not very high TCs. And you can think about how to improve it. People have over the ages. People said, oh, why do we depend on phonons? I can make them attract with very strong Coulomb interactions. So there was a very interesting proposal by someone named Little on organic chains, how to get superconductivity with 1000 Kelvin TC. If you bump this up, right, you make this very small, and now you're your delta is going up now, right? So, but it hasn't come to fruition yet, meaning that particular mechanism of trying to do the pairing in a different way and so on. But yeah.
Maybe a little more abstract, but if people looked at if you could potentially dope heavily enough high band gap semiconductors, because like what omega D scales with band gap, scales with effective.
Yes, indeed. So that's a very interesting thought too. I mean, based on this theory, one would say that if you have a very high phonon energy and you have a high DOS and strong interaction potential, you can increase DC. And people are starting to see, diamond has DC of, I forget, like 6K or something like that. It's not terribly high, but and based on this, if you go to hydrogen atoms and a crystal of hydrogen atom, which people are trying to make as well, right? If you just apply very high pressure, that's very light atoms. So the omega D is very high, and if you have them sufficiently dense, one can get a high TC as well. So people are trying these things, but I would say that so the theory drives some experiments, but then there are experimentalists who don't care much about the theory either. They have discovered superconductors completely away from these theories. In fact, if you, it's almost humbling. But I mean, let me just say, let's not try to speak bad of anything. But the truth of the matter is, where is that TC picture? I forget now. Yeah, the BCS came in 1957. There's no big jump, in the TCs since then. So, it gives us what you call as a cultural education as to, I think we understand why it's doing it. Because if you don't understand why, it's very troubling to do any progress. But people have, people who discovered niobium-3 germanium in this relatively higher TC, they went from very different strategies. Let me just say that strategy is different, but the game was always to increase the number of electrons in the outermost, at the conduction level, at the Fermi level. Always, it's been like that. Not much has been achieved here. And then, the high TC, 1986, right? The high TC, that one, that came out of the blue. I mean, these were perovskite crystals, layered materials. And there was, this theory was completely incapable of giving the microscopic picture. The scheme is still the same. There's some pairing mechanism. What we don't know in high TC is what is the pairing mechanism, right? But everything else, it still has Cooper pairs, have two electron charges, is all the same, right? But exact microscopic picture we don't know. And I think if you read one of the Ginsberg's article, he says that it's a very exciting area because even today you can discover a much higher TC superconductor. His periodic table has a lot of elements, right? And then, which will beat all theories. There's no theory exists for it till today, and next year you get a Nobel Prize for it because this is a big discovery always, right? It's emergent phenomena. You can see that, it would be very difficult to predict a theory like this. It came basically you first. This cannot happen in a single particle picture. Whatever we're looking at it here. By the way, there's one more question. Yeah.
Like these high TC here must have some idea of what they're trying to improve, though, right? Like,
yes,
they're not
they had ideas. They had ideas.
So, what is like what's the theory?
So, basically, the theory was to go to materials. These oxides have very soft phonon mode, so the coupling is lattice distortions are strong, but at the same time they are layered. The electrons are. And the pairing is not singlet, it's more like a D wave. Or something. That being said, I don't think till today there's a complete theory of it. We don't completely understand. But the motivation of the, for Bernoz and Müller who discovered that was not so much from the BCS side as much as, another experimentalist who discovered a lot of these here his name is Bern Matthias. He was at Bell Labs and then at San Diego, and he really did not like any theories at all. He went his own way and he discovered all these, by his own chemical techniques. Essentially, the game was to look at the valence of electrons, how many electrons are in the outermost shell, and what he finds is if it is 6 or 8, you have the highest, increase in TCs. But if it's 7, it's low. So he found these sort of what he calls as empirical rules, but I'm pretty sure there's some science behind it. So going back by that feature, Bednoes and Mueller had some features. Okay. All right, good. Let me outline now we are still sort of far from really explaining the many body part of it. We just made the first step, but it's a very important step, right? And the next step really, I'll work through with you, a little bit, but not in all detail. We'll explain. Actually, it'll give us also the same sort of a band or a gap, or superconducting gap, which will be pretty much similar. But it will give you a little more detail of what is the pair occupation function, how does it change compared to Fermi-Dirac distribution, and then it will give you all the other thermodynamic properties you may want. For example, the lowering of energy of the system and so on. And for this, we want to kind of just use this operator, annihilation creation operator picture, because of the following reason, which I'll give you now. But before that, I just did run some. Okay, so this is just a very simple thing of what we are showing. Here are some of the allowed energies, and here's your 2 over V naught or 1 over V naught here, right? And then you can make your V naught, left hand side as small, rather, actually I'm making it large now, but essentially this is the intersection, and you can always find it. There's always one, so that is it. And now what we are going to see is after we do the BCS theory, what we are going to see is here's an, what is being plotted here is the red dashed line is the single particle Fermi function, occupation function of electrons in a metal. This is the energy with respect to the Fermi energy. Fermi energy is here, Fermi level. So at a high temperature, the Fermi-Dirac distribution is kind of spread out, and then it goes to 1, and then it comes flat, right? If you're deep inside the very, much lower in energy than the Fermi surface, you're always occupied. So this will kind of go to 1. Now the black line here is the pair occupation function, the Cooper pair occupation function. It's slightly different. It also goes through half, and we'll see the expression come out in a few steps now if we get the time. But if I lower the temperature, so let me just explain what I'm doing here. So Fermi function is lower than the pair occupation function here, and it's higher than the pair occupation function here, but they intersect at half, at exactly the Fermi surface, the Fermi level. And then as I lower the normal metal temperature, so I can cross, here's the situation where the red dashed line is a normal metal which has not become superconducting, the occupation function of normal metal states, and the black is the superconducting pair occupation function plotted on the same scale. If you remember, this was lower, right, earlier, so it must actually cross. It's higher now. There's a crossing here, there's a crossing here, there's a crossing here. All 3 places will cross. And there's always a crossing at half, exact half. Okay. In a normal metal, as I lower the temperature, and finally when I go to 0 Kelvin, it will become a unit step, right? And you can see in a Cooper pair, even at 0 K, this black line is going to be like the black line at 0 Kelvin. Right? And you can see there are particles at higher energy here, but this is, remember, this is the kinetic energy. Right? So what I'm trying to say is the 0 Kelvin occupation function of the Cooper pairs actually is not a sharp surface. It has this slope. And why? Because electrons have traded off a little kinetic energy to gain, lowering of potential energy. Do you know what I mean? Because of their motion with the K prime is of pairing, because of this sort of scattering here, because of the scattering here, they're able to lower their energy. So, the system tries to lower its energy by throwing out some particles and creating Cooper pairs and being occupied like this now. Right? So this is the occupation function of the Cooper pairs now, not of single particle electrons anymore. Right? So, okay, so let's go through the steps here. I know it's not much time left today, but let me take you through what was the process, and I'll right. So we now have explained why there should be, a Cooper pair and maybe a linear superposition of them. But what we now want to explain is how there are, all the pairing possible. They all form one coherent state now, not individual, Cooper pairs which are separate from each other, but all their phases are locked. They form one object now. Right? And to write such a wave function, going from the single orbital picture, you can see that let's say there are big N number of electrons on the Fermi surface here within a shell of optical phonon or a Debye frequency. Let's say that's the total number. It's a very large number, 10 to the power 20 or something like that, right? Then I must now form a wave function. For a two-particle state, it was relatively easy. I Slater determinant only two terms. Right? But now you have, n particles. Okay, so you must have a very large number of terms now, right? And now we want to form Cooper pairs, and you can, out of n particles, you can choose 2, and then 2. And how many ways are there to choose it? You can do all the, n over 2 factorial, all that sort of thing, right? There are this many ways to choose, so you must linearly superpose all of them. And if you do this number, this is of the order of 10 to the power 10 to the power 20. That's how many terms you will have instead of this nice term we had here. Right? So that's very difficult. It's hopeless almost, right? And what one of the major breakthroughs of the BCS theory is they are still able to go around the problem and create a wave function, which you can use and write the energies. So and they the way they did it is, you can say it's a trial wave function, and then you apply it to the Hamiltonian, and then see the energy, and you minimize the energy, and and then you find out the coefficients, unknown coefficients. You kind of reduce the number of unknown coefficients. And what we are plotting here is one of those coefficients square, and just explain that now. So okay, so this is kind of a typical problem in many particle physics, that it's very difficult to write the wave function, so you make some inspired guess at this point at this day and age. This is the technique. You kind of make some inspired guesses, and maybe in the future we will figure out some things we don't know today, but in mathematics or something like that. Okay, so before we write down the many particle wave function, let's write down the Hamiltonian. And in the picture of creation and annihilation operators, writing the Hamiltonian is actually extremely easy, much easier than writing out in this way. Right? So what are we really trying to do? Let's write the Hamiltonian first, right? So the Hamiltonian of the system, and we're going to label it as a BCS Hamiltonian, okay, is, what are the single particle energies? The single particle energies are, the sum of these two states, right? And energies of the two states here, right? E0 of k, and I must put two particles in those two states, right? So I must create. Or rather, sorry, single particle states. I'm just looking at this one right now. Forget about pairing at this point. Just this state. So I write Ck dagger, Ck. And then I must also include its spin. This spin is up, but it could be down too, right? Down spin and all that. So spin, I write it as sigma. It could be up or down, whichever one you choose, right? And I sum the whole thing over all k's on the Fermi surface, right? In fact, you can sum it over all internally too, doesn't matter, because that part will kind of go away as a DC value of the energy. So that's your first non-interacting single particle energy term in terms of your creation annihilation operators. These are fermion operators, right? Ck dagger Ck. So they follow the fermion commutation rules, not bosons. They're electron states, single particle electron states, right? And then this process will have the Hamiltonian. Remember, because of this process, what Bardeen-Cooper-Stuff are saying, that my lowering of energy is minus V naught if this process occurs. Right? If this process occurs, the lowering of my energy is minus V naught. And what happened in this process? In the creation annihilation operator, it's delightfully simple. All you care about is what was destroyed and what was created. Right? What was destroyed, these two states. What was created were those two states. And the energy lowering is minus V naught. So the total energy in this picture is just minus V naught times, let's write that. So you annihilated K upspin, right? You annihilated minus k downspin, right? And you created minus k prime downspin, and you created plus k prime upspin. Right? So this is your full process for that particular thing. But then this is also possible for all kinds of k states, so you sum it over all k's as well. Right? So this is your full BCS Hamiltonian that takes into account single particle physics and all correlations at the same time. Right? And now the game we played there, you have to play the game 2 here. This was our real space Hamiltonian for 2 by 2 for 2 particle thing. Here we have a 10 to the power in a very large number of particles. The k sum is running over a very large number of particles. Sorry, forgot k and k prime. There are 2 unknowns here, all possible pairs. So, okay, so so from here now you need a wave function, right? And the wave function, just like you did here, right? You need a wave function, and the wave function is if I find the wave function and I BCS and I do write that, I get the energy, right? That's what I'm after too, right? So at this point, right? So let's look at the wave function, and I'll just outline in the interest of time today. Let's look at just the wave function. What does this wave function represent? Let's look at that first. If I have created just one pair, like we had started with, just one pair with a particular k, with a very particular k, then the pair creation, let's say 0 is my metallic state, meaning no pairs, all Fermi surface, I mean everything below Fermi surface is occupied, everything above is unoccupied. That's 0. That's my ground state. The ground state here is not vacuum. Ground state is a normal metal state. 0, right? This has a lot of states in it, a lot of orbitals. They're all occupied, and some of them above the Fermi energy are unoccupied. That's your ground state here. And now on the ground state, I must apply, I must create with upspin, and I must create a Cooper pair. So k and minus k, upspin and downspin. Right? That created one Cooper pair like that. Right? It's a pair now, right? Pair wave function. And so that's your just one Cooper pair here with a particular k. And then I can write the total state of the system as a situation where there is no Cooper pair formed plus a situation where there is a Cooper pair formed. It's a linear superposition, and the way you write that is uk, a coefficient which we don't know, plus vk times that. These are the 2 coefficients we don't know, analogs of my g of k here. Right, this makes sense. I mean, this is how I'm writing it. It's a sum of unoccupied Cooper pair and occupied Cooper pair. If you have no Cooper pairs at all, if you're normal metal state, Vk is 0, this is 1. Right? As you start increasing the number of Cooper pairs, this goes up, this goes down. And there must be some sort of a balance between the two. And we'll see that the balance will come as uk square plus vk square is equal to 1. We'll see that soon. OK. Now what you see.
This will be summed over k?
Actually, yeah. I'm just writing for just one pair. You're right. But now I want to create the many-body condensate. Let me be a little more accurate. This ordering here is a little important, so it should be actually written as plus k and up here. It's actually a little important. I just want to make sure I'm accurate about it. So here what you see then is it looks like uk plus this operator. If you look at your assignment 2, you have defined as bk dagger. This is the operator you have defined as bk dagger. It's just a composite of 2 fermion states, and vk and bk dagger acting on 0. And what also kind of notice is if these are fermion states, if you try to do bk dagger square, you will get a 0. Cube will get a 0, and so on. It only survives till the square. If it only serves as a linear term, it doesn't go any further, right? So you can also write this as e to the power and alpha times bk dagger, where bk dagger is the pair operator, Cooper pair creation operator, right? Times a ground state. You can also write it like that. Why? Because e to the power alpha is that is equal to 1 plus some constant alpha k, let's say it's a constant, times bk dagger plus nothing else. You can find out your coefficients and what is alpha. It just stops after the first term. That's all there is. And this is what's called a coherent state in quantum mechanics. I mean, basically a state with some very interesting properties. I don't want to kind of get into that. So I just want to point that you can write it like that. And this is where this will lead to the fact that your full wave function is written as, if you remember, e to the power I theta. We had talked about that. The fact that the phases, it will lead to that sort of picture. Yeah. Okay, good. So this is just we just got started on this, but I didn't want to kind of go through in the next class and finish it perhaps there. But once you understand that part, the total wave function is really a product of all k states, as you said. It's a product of all these things, and it's a kind of a big product. But amazingly, if you write it in this way, you can actually, it works out just fine. If you realize that this is formed by, a coherent superposition of all k states, you will be able to calculate the energy and what is the v of k squared and what's the probability, and finally you'll be able to get the gap. Just kind of in a few steps. But this is kind of the genesis, at least from the from this picture. You can see how it's built up. The full wave function is the product of all states now. Product of all these, and the operators work in a nice way that it shrinks, and because they're fermions, many terms go to 0, and you get your energy is going to be in terms of just uk squares and vk squares, just like you had here in terms of these unknown coefficients gk's. Where is it? Yeah, it's just like that. So. But it's a many particle wave function now. So okay, good. So let's stop here. I'm a little out of time, and we'll. I didn't get to the integer quantum Hall effect, but I will in the next assignment, which is supposed to be posted probably tomorrow. You have a few things you can work on this, but I'm just pointing out some of these steps for you at this point. Good. Thanks.